Now, previously, we have been solving systems of linear equation using Gauss-Jordan elimination. That is, we are making use of the elementary row operation. And we also have solved the system of equation using matrix operation, as well as using matrix inversion. Now, another technique on how we can solve a system of equation is using what you call Cramer's rule. Theorem 3.11 gives us Cramer's rule. It states that if a system of n linear equations in n variables has coefficient matrix A with a non-zero determinant, then the solution of the system is given by the following. The first variable x sub 1 is equivalent to the determinant of A sub 1 over determinant of A, where A is the coefficient matrix, and the second variable x sub 2 is equivalent to the determinant of A sub 2 all over determinant of A, up to the last variable wherein x sub n is equivalent to the determinant of A sub n over the determinant of A. Now, where the ith column of A sub I is the column of constants in the system of equation. So meaning if we will have A1, this means that we are replacing column 1 by the column of constants. If we will have A2, that means we are replacing the second column by the column of constants, and for A sub n, we are replacing the nth column by the column of constants. Now, say in example number 4, solve the system of linear equation using Cramer's rule. So since we're asked to solve the system of linear equation for x, we know that x is equivalent to the determinant of A1 over the determinant of A. So we have here the determinant of A1 over the determinant of A. We already know the determinant of A, say it is given here as 10. So we only need to find the determinant of A1. So we will have the matrix wherein we replace the entries for column 1 by 1, 0, 2. So we will have here 1, 0, 2, and then copy the, simply isolate all the coefficients of y and z. So we will have here 2, 0, negative 4, and then we will have here negative 3, positive 1, and positive 4. Now notice that in our row 2, we will have 2 zeros. So we can perform our cofactor expansion along row 2. Since we have 2 zeros there, we will have 4/5. So x is equivalent to 4/5. Now let's say, aside from x, let us also solve for y as well as for z. So how do we solve for y? So we will have y is equivalent to the determinant of A sub 2 all over the determinant of the coefficient matrix A. How do we find the determinant A sub 2? First of all, we need to replace the column 2 entries by the column of constants and simply copy all the entries for column 1 and column Z in the coefficient matrix. So you will have here negative 1, 2, 3, and then replace the second column by 1, 0, 2, and then copy the entries in, the last column, which is negative 3, 1, and 4, which are the coefficients of Z. And then since we know that the determinant of the coefficient matrix is 10, so we have here 10. Now we can choose to get a cofactor expansion, say at column 2. So this is negative 15 over 10 divisible by 5, and the answer is negative 3/2. Okay, so y is equivalent to negative 3 over 2. Now to solve for z, this is equivalent to the determinant of A sub 3 all over the determinant of the coefficient matrix A. Again, we already have the coefficient, the determinant of the coefficient matrix A, which is 10, and we only need to find the determinant of A sub 3. So A sub 3 is a matrix wherein the column 3 has been replaced by the column of constants. So copying all the entries in column 1 and column 2 in your coefficient matrix. And then I will have here my 1, 0, 2. And again, I can see zeros in row 2. So performing a cofactor expansion at row 2. So I'll have here negative 8 all over 5. So this will be my z. So the solution is given by 4/5, negative 3/2, and then negative 8 over 5. Now, I can try to check if this answer is correct by substituting it to the system of equation.